somewhere in the quiet dark beyond our sun, there are worlds so strange that, until recently, no one believed they could exist. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. Tonight, we drift out past the planets we know, past the familiar circle of rocky inner worlds and gentle gas giants, into a wider sky where the rules seem to soften and bend. Out there, planets do things our textbooks never prepared us for. They rain glass. They glow with molten oceans. They wander alone without a sun to circle. Imagine for a moment lifting up and away from Earth. The blue curve of the planet falls behind you. The moon, pale and pocked, slips past. The sun shrinks until it is just one light among many, a yellow point lost in a slow, turning river of stars. This is our galaxy, the Milky Way, a great spiral of suns so vast that light itself needs 100,000 years to cross it. And around so many of those suns, quietly, patiently, planets are circling. We have already found more than 5,000 of them. We suspect there may be hundreds of billions more. That number alone is hard to hold in the mind. More worlds than there are grains of sand on a long, quiet beach. More worlds than there are heartbeats in a human lifetime. And the strange truth is that almost everything we have found out there looks unlike anything in our own solar system. We expected polite copies of Earth or familiar gas giants like Jupiter. Instead, we keep finding worlds that, by the old rules, should not exist. There are planets larger than Jupiter that orbit their stars in less than a single Earth day, skimming so close to the fire that their upper atmospheres bleed away into space. There are worlds so light and puffy that, if you could find an ocean big enough, they would float on it like a cork. There are planets that drift between the stars with no sun at all, wrapped in eternal darkness, perhaps with hidden oceans tucked beneath thick skins of ice. There are worlds where the rocks themselves are molten on one side and frozen on the other, because the same face always stares at their star. And here is where the mystery begins to settle in. We do not see these planets directly, not really. They are too faint, too far, too lost in the glare of their stars. we learn about them through whispers. A tiny dimming of starlight as a world passes in front. A faint wobble in a star's motion as a planet tugs it gently from side to side. A small shift in color when light filters through an alien sky. From these whispers, we build pictures. From these pictures, we tell stories. But the whispers are noisy. The data is faint. And so the deeper question, the one that will sit with us across the long hours of tonight, is this: how many of these strange worlds are truly as strange as we think they are? And how many are simply our best guesses from incomplete signals? A planet described as a glittering diamond may be something else entirely once we look more closely. A world called an ocean planet may turn out to be dry. A superpuff lighter than cotton candy may, on closer study, be a smaller world wrapped in a great halo of dust. Some researchers feel confident that the strangest planets are real, that the universe is simply more inventive than we ever imagined. Others wonder if many of these wonders will quietly shrink, soften, or vanish as our instruments grow sharper. Both views are honest. Both views are reasonable. The evidence, for now, is incomplete. That uncertainty is not a problem to solve tonight. It is the very thing to rest in. The sky above us is full of half-seen worlds, sketched in faint light, half guessed at, half dreamed. Some of them may be exactly as we describe. Some of them may be stranger still, in ways we have not yet imagined. And some, perhaps, are gentler illusions, ghosts in the data that will fade as we learn to look more carefully. So settle in. Let your shoulders soften. We are going to drift slowly through 24 quiet windows onto the strangest planets ever found. We will not try to settle the mystery. We will only sit beside it, the way you might sit beside a wide, dark sea, listening to it move. Content not to know exactly what lies beneath. Before we wander further out among the strange worlds, it helps to settle into one of them. A single planet, well studied, that gives us a feeling for just how odd a world can be, while still being, in some sense, ordinary. Astronomers call it HD 189,733b. The name is not poetic, but the place itself is something out of a fever dream. It sits about 64 light years from us, in the direction of the small constellation called the Little Fox. By cosmic standards, that is close. If our galaxy were a city, this planet would be just down the street. And yet, we have never seen it directly. We have only watched the tiny dimming of its star as the planet passes in front, and felt the faint pull it gives that star as it swings around. From those whispers in the data, we have built a picture of the world. It is a gas giant, about the size and weight of Jupiter, the largest planet in our own solar system. But unlike Jupiter, which sits far from our sun in slow, cold orbit, this planet hugs its star. It circles so close that 1 full year there lasts only about 2.25 Earth days. Imagine a birthday every 50 hours. Imagine a sky where the star fills a huge portion of the view, a glowing wall of light, never setting, never softening. Being that close has consequences. The planet is tidally locked, which simply means the same side always faces the star, the way the same face of our moon always faces Earth. So 1/2 of the world burns under endless daylight. The other half drifts in endless night. On the day side, temperatures climb to something like 1,200 degrees Celsius. That is hotter than molten lava, hotter than the inside of a kiln used to fire pottery. On the night side, it is cooler, but still hundreds of degrees above anything we would call comfortable. Now comes the strange part, the part that earned this world its quiet fame. When astronomers looked at the light passing through its upper air, they saw a deep blue color. Not the soft blue of our own sky, which comes from sunlight scattering in nitrogen. The blue of HD 189,733b appears to come from something else entirely. The leading idea is that the clouds there are not made of water vapor. They may be made of silicate particles. In plain language, tiny grains of glass. If that picture is right, the sky on this world is a haze of microscopic glass beads, suspended in a hot, thick atmosphere, and the winds, driven by the gulf between the scorching day side and the cooler night side, are believed to scream around the planet at speeds of around 8,000 kilometers per hour. That is several times faster than the speed of sound on Earth. In those winds, the glass particles would not fall gently downward. They would be hurled sideways. A rain that does not so much fall as fly. That, at least, is the picture painted by one set of measurements and one set of models. Other researchers urge caution. The signal we read is faint. The blue color could come from a different mix of chemicals. The wind speeds are inferred, not directly clocked. The clouds might be thinner than the dramatic descriptions suggest, or arranged in patches rather than a global storm. Some models even propose that the deepest layers are clearer than we think, with the glassy haze sitting only near the top, until a future telescope can study the planet in finer detail. Both the dramatic version and the gentler version remain on the table. What is not in doubt is the basic shape of the place. A puffy ball of hydrogen and helium, about 1.1 times the mass of Jupiter, scorched by a star that is itself a little smaller and cooler than our sun. An atmosphere that absorbs and re-emits enormous amounts of heat. A surface that in any earthly sense does not exist. If you fell toward this world, you would pass through layers of thickening gas, growing hotter and denser, until the very idea of falling lost its meaning. It is a useful place to begin. This strange blue giant, because it shows how much can be true at once. A planet can be massive and familiar in its bulk, yet alien in every detail. It can sit close enough to study, yet far enough to keep most of its secrets. And it reminds us that the strangeness we are about to explore is not invented. It is read carefully and uncertainly from the faintest flickers of starlight. Among all the strange worlds we have found beyond our sun, none are quite as puzzling as the puffed-up giants. They are larger than Jupiter, sometimes nearly twice as wide, yet they weigh almost nothing. If you could somehow gather one of these planets into a giant cosmic scale, you would find it lighter than cork, lighter than balsa wood, in some cases as airy as cotton candy spun at a country fair. Astronomers actually call them super puffs, and the name fits. The question of how such ghostly worlds came to exist sits among the gentlest mysteries in planetary science. to picture one, imagine a soft pink and gold sphere drifting in the dark, glowing faintly in the light of a distant star. Its outer edges fade into a haze so thin that the line between planet and space seems almost blurred. If you could push your hand through the upper layers, you would feel only a warm whisper of gas. Down inside, somewhere beneath those endless thin clouds, there must be a heavier core. But the gas around that core is spread so wide that the whole world becomes one of the lightest places we have ever measured. How does such a thing form? The honest answer is that nobody yet agrees. One idea begins in the early days of a young star, when a flat disk of gas and dust still circles it like a slow record. Small grains stick together. The clumps grow into pebbles, then boulders, then rocky cores. If one of those cores swells to about 10 times the mass of Earth before the gas runs out, it can pull in a thick blanket of hydrogen and helium. Normally, that blanket would settle and shrink over time. The puzzle is that superpuffs never seem to have done that settling. Their atmospheres remain fluffed up, as if frozen in a younger, looser state. One theory suggests these planets formed far away from their stars, out in the cold edges of the disk, where gas behaves more gently. There, a young world could grow a swollen envelope without the heat of a nearby sun pressing on it. Later, some slow gravitational nudge from another planet might have eased it inward. Into the warmer light we see it bathed in today. In that view, the puffiness is a leftover from a quieter childhood farther out. Another idea points to internal heat. If the inside of the planet still glows from the friction of its formation, that warmth could keep the atmosphere lofted, the way warm air swells a hot air balloon. As long as the core stays hot, the envelope stays large. In that picture, the puffiness is a passing phase. Given enough time, perhaps billions more years, these worlds might cool and slowly shrink into more ordinary gas giants. We are simply lucky to catch them in a strange, brief moment of their long lives. A third possibility is stranger still. Some researchers wonder whether we are misreading the data altogether. When a superpuff passes in front of its star, light filters through its outer haze. That haze can make the planet look much larger than its true solid bulk. If thick layers of dust and tiny crystals float high above the real cloud tops, the planet might only seem enormous while actually being smaller and denser inside. In that case, superpuffs would not be lighter than Cork at all. They would simply wear a very generous coat. Each theory carries weight, and each leaves something unexplained. The first cannot easily say why so many puffed worlds sit so close to their stars now. The second struggles to account for the youngest examples, which already seem too puffy for their age. The third would tidy the numbers, but cannot yet explain what those high hazes are made of. So the question hangs there in the quiet, waiting. What we do know is that these worlds invite a particular kind of wonder. They challenge the simple picture in which planets are dense, solid things you could stand on or sink into. A superpuff is almost more atmosphere than planet, a faint cloud held together by gravity and patience. In the soft pastels of artist renderings, they look like wisps caught between sky and dream, hardly real, barely there. Somewhere out in the dark, a young star is shining on a world we may never visit, a world spread out and ghostly in its own thin glow. How it grew so light, why it has not yet collapsed into something firmer. Whether it ever will, these remain open questions. For now, the puffed giants drift on slowly in the long arms of their orbits, keeping their secret in the silence between the stars. Somewhere in the dark, drifting around a quiet star many light years away, there may be a planet whose insides are made of diamond. The idea sounds like a fairy tale. The science behind it is more careful, more strange, and still very much unsettled. To wonder about it, we have to think about what planets are made of and where those ingredients come from in the first place. Every world in the sky is built from leftovers. When a star dies, it scatters its insides into space. Some stars puff off their outer shells in soft, glowing clouds. Others end in sudden, violent collapse, seeding the dark with iron, carbon, silicon, and oxygen. Those scattered ashes drift for millions of years. They cool, they clump, they become the dust and gas from which new stars and new planets are born. The iron in your blood and the iron in Earth's hot core both came from dying stars. The same is true for every planet we have ever found. What changes from world to world is the recipe. A young star is wrapped in a flat disk of dust and gas. Inside that disk, the mix of elements can tilt one way or another. If a star formed from a cloud rich in oxygen, its planets tend to be rocky in the way Earth is rocky, full of silicates, the mineral family that gives us sand, granite, and the gray stones under our feet. But if a star formed from a cloud richer in carbon than oxygen, the chemistry shifts. Carbon takes over, and carbon, under enough pressure, can become something remarkable. This is where the diamond worlds enter the story. Some researchers have wondered whether certain exoplanets born around carbon-rich stars might have mantles made not of silicate rock, but of carbon compounds. Deep inside such a world, where the pressure is crushing and the heat extreme, that carbon could be squeezed into the same crystal structure we know on Earth as diamond. Layers of it, maybe thick layers. A planet with a heart of gemstone, hidden forever beneath a dark surface. One world, in particular, drew this kind of attention some years ago. It is a small, hot planet orbiting very close to its star, and early measurements hinted that its parent star carried more carbon than oxygen. From those numbers, a few researchers sketched out a possible interior rich in carbon and diamond. The picture was beautiful. It was also fragile. Later measurements of the same star suggested its carbon was not as high as first thought. The diamond planet idea did not vanish, but it softened into a maybe. It became one model among several, not a fact carved in stone. That is the honest shape of this mystery. We rarely see a planet's insides. We see a tiny dip in starlight when the world passes in front of its sun. We see a faint wobble in the star's motion. From those whispers, we guess at mass and size. From mass and size, we guess at density. From density, we guess at what the planet might be made of. Each guess is a small leap, and the leap from this planet is dense to this planet contains diamond is a long one. Several recipes can give the same density. Iron and rock, rock and water, carbon compounds in unfamiliar mixes. The numbers alone cannot tell them apart. Still, the wider idea holds together. The universe really does build planets from whatever its parent cloud happens to carry. Some clouds are rich in metals. Others are rich in carbon. Others carry strange amounts of magnesium, sulfur, or sodium. The water in our oceans, some scientists think, was delivered partly by comets and ice-rich rocks long after Earth itself had formed. Other worlds may have gotten their water in completely different ways, or barely gotten any at all. The same elements, mixed in different proportions, give rise to wildly different skies. So when we picture a possible diamond world, we are picturing one ending of a very old story. A star long dead threw its carbon into the dark. That carbon drifted, cooled, gathered. A new star lit up. A disk formed. Grains stuck to grains. A planet grew. Deep inside it, pressure did the slow, patient work of turning soft carbon into hard crystal. Maybe. We do not know for sure. The measurements are noisy. The models compete. Other researchers think these worlds are mostly ordinary rock with only thin carbon layers, or no diamond at all. For tonight, the question can stay open. Somewhere out there, a planet may be quietly hiding a treasure no eye will ever see. Or it may not. Both possibilities live in the same starlight. Drift now into a strange thought. Somewhere, far from any star, a world is moving through the dark. It has no sunrise. It has no sunset. It has no warm orange light falling across its clouds. It simply travels alone through the deep night between the stars. Astronomers call these worlds rogue planets. They are planets without a sun. Some may have been born this way, forming from collapsing gas in quiet pockets of space. Others may have been thrown out of their home solar systems long ago, tossed away by the gravity of a larger sibling. We are not sure which path is more common. The question remains open. Think of the forces that shaped such a world. In a normal solar system, a star sits at the center, pulling everything inward with steady gravity. Planets feel that pull. They settle into smooth orbits, warmed on one side, cooled on the other, held in a long, patient dance. A rogue planet feels none of that. The nearest stars are too far away to tug on it in any meaningful way. It floats free, carried only by its own old momentum from whatever event set it adrift. Yet gravity has not abandoned these wanderers. They still hold themselves together. Their own mass pulls inward, squeezing their cores under tremendous pressure. Deep inside, that pressure becomes heat. A large rogue planet, especially a gas giant, can stay surprisingly warm for billions of years just from this slow inner squeeze. The heat does not come from a star. It comes from the planet itself, leaking outward from its hidden interior. Some researchers wonder whether this inner warmth could be enough to keep a thin ocean liquid beneath a thick shell of ice. Imagine that for a moment. A dark, sunless world, a frozen crust on the outside, glassy and still. And below, hidden from any sky, a quiet sea, warmed only by the slow heartbeat of the planet's own gravity. Whether such oceans truly exist on rogue planets is unknown. We have no way yet to look inside one. The idea sits in the space between possible and proven. Other forces sculpt these wanderers in subtler ways. Magnetic fields, if the planet has a churning metal core, may still glow faintly with their own auroras. There is no solar wind to push against, but cosmic rays from distant, exploded stars drift through the galaxy in every direction. When those particles strike a rogue planet's upper air, they may light it from above in pale, ghostly curtains. No one has ever seen such an aurora. The thought is only a guess, drawn from what we know of magnetic worlds closer to home. Radiation, in the usual sense, barely touches these planets. Without a nearby star, there is no harsh ultraviolet light scouring the surface. There is no warm infrared bath. The temperature outside is brutally cold, often only a few tens of degrees above absolute zero. Yet the deep interior may be thousands of degrees. A rogue planet is a study in contrast. A frozen shell wrapped around a hot, slow-beating heart. Tidal forces, which shape so many worlds in normal solar systems, hardly act on a rogue at all. There is no star pulling on one side more than the other. There is no neighboring planet close enough to flex its rocks. The wanderer drifts in near-perfect stillness, save for whatever moons it may carry with it. And yes, moons may travel along. When a planet is flung from its home system, its moons can sometimes come too, locked in place by the planet's gravity, a tiny family moving together through the long dark. How many of these lonely worlds drift through our galaxy? Some surveys suggest there may be billions. Others place the number lower. The detection methods are difficult. A rogue planet gives off almost no light. Astronomers usually spot them only when one passes in front of a distant star and bends its light, a brief flicker called microlensing. Each flicker lasts only hours or days. Then the wanderer is gone again, swallowed back into the dark. So we do not really know how many rogues there are. We do not know how warm their interiors stay. We do not know if any of them carry hidden oceans or thin, glowing skies of cosmic ray light. We only know that the forces of gravity and pressure and slow internal heat continue to shape them quietly, with no one watching. Picture one of them now as you settle deeper into rest. A dark sphere turning gently far from any sun. Snow on its surface, perhaps. Stillness everywhere. And somewhere below the ice, a quiet warmth, holding on through ages of silence. Imagine a world where the sun never sets. Not for a day, not for a year, not ever. One side of the planet faces its star forever, baked in unending light. The other side faces the dark, frozen in a night that never ends. These are tidally locked worlds, and to understand them, you need to feel just how strange that arrangement really is. Picture Earth as we know it. Our planet spins like a slow top, turning once every 24 hours. That gentle spin gives us sunrise and sunset. It spreads the warmth around. It mixes the air. It is so normal to us that we forget it is happening at all. Now picture our moon. The moon is tidally locked to Earth. The same face always points toward us. The far side never turns our way. We did not even see it until a spacecraft drifted around the back in 1959. For all of human history before that, half of our nearest neighbor was hidden. Most of the small rocky exoplanets we have found orbit very close to their stars, so close that the star's gravity has done to them what Earth's gravity did to the moon. It has slowed their spin until one side locked in place. To feel the scale of this, try a small thought. Shrink a star like our sun down to the size of a beach ball, about 2 feet across. Earth, at that scale, would be a small pea sitting 215 feet away, about 2/3 the length of a football field. That is comfortable. That is room to breathe. Now place a tidally locked world in that same model. Many of them orbit red dwarf stars, which are smaller and dimmer than our sun. Shrink one of those stars to a softball. The planet would sit only a few feet away, close enough that you could reach out and touch it, close enough that the star fills nearly the entire sky on the day side. If you stood on the day side of such a world, the star would hang in one spot above you forever. It would never rise. It would never set. It would never even drift. The shadows under your feet would not move. A stone you set down at noon would still have the same shadow 1,000 years later. The temperature gap between the two halves could be enormous. On the day side, the surface might sit hot enough to melt lead. On the night side, the air itself could freeze and fall like snow. Between them runs a thin ring of twilight, a band of permanent dusk, where the star sits low on the horizon and never moves. Some researchers wonder if that twilight band is the only place such a world could be friendly to life. Not too hot, not too cold, just a narrow strip of forever evening, perhaps a few 100 miles wide. One idea is that winds would race from the burning side to the frozen side, carrying heat across the planet in fierce, steady rivers of air. Another idea suggests the atmosphere would simply collapse, freezing onto the dark hemisphere as solid ice, leaving the day side bare. We do not know which picture is correct. We cannot yet see the surfaces of these worlds. We only catch faint hints in the light that filters through their atmospheres, and that light is dim and noisy and hard to read. The numbers can feel hard to hold in your mind, so try this. The closest tidally locked candidate we know orbits a star just over 4 light years from us. Light, the fastest thing there is, takes more than 4 years to cross that distance. A modern spacecraft would take tens of thousands of years, and that is the nearest one. There may be billions more across the galaxy. Red dwarf stars are the most common kind of star, and most of their planets sit close enough to lock in place. If life exists on rocky worlds out there, it likely lives on a planet with a permanent day and a permanent night. Our own daily rhythm, the rising and setting we take for granted, may be the rare arrangement. It is worth sitting with that thought as you rest. Somewhere right now, on a world we have barely begun to study, a star is hanging motionless in a violet sky. A shadow has been pointing the same direction for 1,000,000 years. A wind is blowing in one steady direction, never shifting, never pausing. Whether anyone or anything stands in that twilight to feel it, we cannot say. The question stays open. The light from those worlds is still arriving, and we are still learning how to read it. Picture yourself floating above a world unlike any in our own solar neighborhood. It is larger than Earth, smaller than Neptune, and wrapped in a thick blanket of pale hydrogen mist. The light from its sun arrives soft and golden, scattered through layers of haze that glow like a lantern wrapped in silk. Beneath that haze, something even stranger waits. A vast, dark ocean. And under that ocean, a shell of ice so hot it would melt steel on Earth. These worlds are sometimes called Hycean planets. The name blends the words hydrogen and ocean. They are still only a theory, a possibility researchers are testing with patient observation. Some astronomers believe a handful of known exoplanets may belong to this strange new family. Others are not convinced. The signals are faint. The data is noisy. The debate is gentle but ongoing. If the theory holds, the surface of such a world would feel almost dreamlike. There would be no shoreline, no continents, no rocks breaking the horizon. Only water stretching in every direction, dark as wet slate. The ocean might be hundreds of kilometers deep, far deeper than any sea on Earth. Waves could rise slowly under the heavier gravity, rolling like soft hills rather than sharp peaks. The water itself might be warm, even hot, kept liquid by the crushing weight of the atmosphere above. That atmosphere would be the first thing to startle you. Hydrogen, thick and pale, with traces of methane and carbon dioxide mixed in. The sky would not be blue. Some models suggest a soft amber tone near the horizon, fading to a deeper rust above. Clouds of water vapor might drift in long bands, lit from beneath by the glow of warm seas. There could be lightning, slow and silent at this distance, flickering inside cloud towers that climb for tens of kilometers. Now imagine sinking down through the warm water, past where light can reach, into a pressure no submarine could survive. After many kilometers, you would not hit a rocky floor. You would meet something stranger, a layer of ice, but not ice as we know it. On Earth, ice forms when water gets cold. On a Hycean world, the deep ice forms when water gets squeezed. Under enormous pressure, water molecules pack into dense crystal patterns even when the temperature stays high. Scientists call these forms by numbers. Ice VII. Ice X, some may exist in a strange in-between state, half solid, half flowing. The surface of this hot ice would be smooth and glassy in places, rough and ridged in others. It could glow faintly with the heat trapped below. What lies beneath that ice shell is one of the quieter mysteries of planetary science. There may be a rocky core, locked away forever, never touched by the ocean above. There may be slow currents of even denser fluid, churning under pressures we cannot easily picture. Some researchers wonder if the boundary between hot ice and warm water could be a place where simple chemistry, the kind that might lead to life, could find a foothold. Others argue the temperatures are too extreme, the pressures too crushing, the chemistry too thin. The question stays open. Floating above the surface, you might never know any of this. You would see only the soft horizon, the endless rolling water, the amber sky. A small moon, if one existed, might rise as a pale disk through the haze. The sun would look swollen and dim, depending on how close the planet sat in its orbit. There would be no birds, no shoreline sounds, only wind moving across water, and water moving against itself in a slow rhythm that seems older than thought. It is worth saying again that no one has yet confirmed a Hycean world. A few candidates have caught the attention of telescopes. One, named in the catalog as a sub-Neptune, several hundred light-years away, showed faint hints of certain gases in its atmosphere. Some scientists read those hints as evidence for a warm ocean below. Others read the same data and see a hot, dry, hydrogen-rich world with no ocean at all. Both teams use careful methods. Both could be partly right. The instruments are simply not yet sharp enough to settle the matter, so the image stays soft at the edges. A world that might be there, an ocean that might roll beneath an amber sky, a floor of hot ice that might cradle that ocean from below. Maybe these places are common in the galaxy. Maybe they are rare. Maybe the whole category will dissolve as better telescopes look closer. For now, the picture floats in the imagination, half real, half waiting, the way many of the strangest worlds first ap. Far from our quiet corner of the galaxy, there is a world that astronomers sometimes describe in terms that belong less to a planet and more to a chemistry set left burning in a closed room. It orbits a small, cool star, and it is roughly the size of Neptune. Its name is a string of letters and numbers, but its character is unforgettable. Researchers studying its atmosphere have detected hydrogen sulfide, the gas that gives rotten eggs and old matches their sharp, sulfurous smell. If you could somehow stand in its high clouds and take a breath, the air would carry the scent of something burning and spoiled all at once. That detail alone makes the world strange. But what makes it truly mysterious is what we cannot see. The visible atmosphere is only the outer skin of the planet. Below that thin layer of swirling gases lies a deeper region we can only model in theory. Some researchers think the interior may be a slow, hot soup of hydrogen, helium, and heavier elements pressed into states of matter that have no name on Earth. Others wonder if there is a core of rock and metal buried far below, or perhaps a layer of strange, dense ice that never freezes the way water does in a cold glass. The trouble is, we have no way to see down there. Every observation we have of this world comes from light. When the planet passes in front of its star, a little of that starlight filters through the upper atmosphere on its way to us. That filtered light carries fingerprints, tiny dips at certain colors that tell us which gases are present near the top. Hydrogen sulfide leaves one such fingerprint. So does water vapor. So do other molecules, but the deeper layers absorb and scatter the light long before it ever reaches the high clouds. And so the interior stays hidden, the way the bottom of a deep lake stays, hidden under sunlit ripples. This leaves us with competing pictures of what the depths might hold. One idea is that the planet is mostly gas all the way down, with hydrogen and helium growing thicker and hotter until they behave almost like a liquid metal. Another idea is that the planet is mostly water and other ices, wrapped in a thinner skin of gas, more like a vast, warm ocean buried beneath the clouds. A third idea is a middle path, with layers of each, stacked in ways we cannot quite predict. None of these pictures has been confirmed. None has been ruled out. The smell of burning, if you can call it that, hints at active chemistry. Hydrogen sulfide is fragile. Strong starlight tends to break it apart over time. For us to detect it at all suggests that something is replenishing it from below. Some researchers wonder if deep convection, slow, churning currents inside the planet, is dredging sulfur compounds up from hotter, hidden regions and feeding them into the visible sky. Others think the gas may be left over from the planet's formation, somehow preserved against the slow erosion of starlight. The two ideas point to very different interiors, and we cannot yet tell which is closer to the truth. There is also the question of how typical this world really is. The instruments that found its sulfurous signature are sensitive, but they are not perfect. The signal is faint. The data is noisy. A few researchers have asked whether the detection itself might be partly an artifact of how we read the light. A pattern our methods are prone to find, even when it is not quite there. Most agree the molecule is present. The exact amount and what it implies about the depths is still being debated in careful, patient papers. What is certain is that the planet is unlike anything in our solar system. Neptune has hints of strange chemistry too, but nothing quite this sharp, this acrid in our imagination. And the more carefully we look at worlds around other stars, the more we find that the familiar categories, rocky, gassy, icy, start to blur. A planet can smell of burning and still be calm. A planet can hide an ocean under clouds of poison. A planet can can be both gentle and impossible at once. So tonight, picture that distant world, a pale, hazy disk turning slowly against the deep black. High clouds shifting in patterns we will never witness up close. Beneath them, layer upon layer of pressure and heat and chemistry we can only guess at. Somewhere in those depths, the answer is waiting, the true shape of the interior, the source of the strange scent, the structure that keeps it all in balance. We are still learning how to listen for it. Somewhere in the dark, far beyond our small blue world, there are planets that glow. Not by reflected starlight, the way our moon shines. They glow because half of their surface is molten rock. These are the lava worlds, and they may be the strangest cyclical objects we have yet found in the sky. Picture a planet so close to its star that one full orbit takes only a day or two. Its year is shorter than our weekend, and because it sits so near to that furnace, gravity has slowed its spin until one face is locked toward the star forever. On that side, the temperature can climb high enough to melt stone. Rivers of magma may pool across the surface. Oceans of liquid rock may shimmer red and orange beneath a sky that never darkens. The other side, turned forever away, may be cold and black, frozen into a brittle crust no eye will ever see lit. That contrast is where the cycles live. On a world like our own, day turns into night, summer into winter. On a lava world, the cycle is not in time, but in place. You could stand at the boundary between scorching dayside and frozen nightside, and the difference would unfold not over hours, but over footsteps. Some researchers wonder whether winds powerful enough to bend physics carry heat from the bright hemisphere toward the dark one. Models suggest these winds might race faster than the speed of sound, sweeping vaporized rock around the globe in great burning rivers of air. Other models suggest the heat barely moves at all, and the two hemispheres remain locked in their separate fates. The truth is, we cannot yet see clearly enough to know. There is another rhythm at work here, slower and deeper. Tides. A planet pulled this close to its star is squeezed and stretched by gravity in ways that never quite let it rest. The crust may flex. Magma chambers may bulge and contract with each tight orbit. Some scientists believe this constant tidal kneading could fuel volcanoes more violent than any in our solar system. Eruptions might tower hundreds of kilometers high, throwing molten droplets into the thin atmosphere where they cool into a fine mist of glass before falling back down. Other scientists are more cautious, suggesting that without solid measurements of the surface, we are only painting pictures with our equations. One candidate world has become a favorite subject for these wonderings. Astronomers detected it as a tiny dimming of starlight, repeating with a heartbeat shorter than 2 earthly days. From that flicker, and from careful study of the warmth coming off its surface, they pieced together a portrait of something that should not be able to exist for long. A planet too hot, too close, too restless. And yet, there it is, orbiting in its tight little circle, glowing on one side, brooding on the other. What does a day look like on such a world, if day is even the right word? On the bright hemisphere, the star would hang motionless in the sky, never rising, never setting. Its light would be so close and so fierce that the ground itself would seem to pour out heat back into the air. Perhaps the magma oceans would have currents, slow and luminous, shaped by the gravity of the unseen star above. Perhaps the surface would freeze and crack and melt again as wind patterns shifted overhead. We do not know. We can only sketch the possibilities from a distance of many light years. There is also a quieter mystery hidden inside these molten worlds. They may not always have been so hot. Some researchers wonder if lava planets begin their lives further from their stars, with more ordinary surfaces, and only later spiral inward to be remade by the heat. If that is so, then each glowing hemisphere is the record of a long migration, a cycle of orbital change written in melted stone. Others suggest these worlds may have formed close to their stars from the very beginning, born already burning. Both stories fit the evidence we have. Neither has yet been ruled out. So the rhythms of a lava world are not the rhythms we know. There is no dawn. There is no winter. There is only the slow, ceaseless pulse of tides, the silent shifting of magma, the wind that may or may not stir, the eruptions that may or may not be cycling beneath an alien sky. Picture it now, soft and far away, glowing gently in the dark like an ember tucked into the corner of the galaxy. Then let it cool in your mind and drift onward toward the next strange world waiting in the quiet. Picture standing on a world where two suns rise together. One burns a warm gold. The other glows a softer orange, or perhaps a deep ember red. Their light mingles on the ground, casting double shadows that drift and overlap as the day moves on. This is not science fiction. Planets like this are real, and we have found dozens of them so far. Astronomers call them circumbinary planets. The name simply means a planet that circles two stars at once, instead of just one. The two stars orbit each other in a close gravitational dance, and the planet swings around the pair from farther out. For a long time, many scientists thought such planets could not form at all. The reasoning seemed sound. Two stars whirling around each other should stir the surrounding dust into chaos, flinging away the building blocks before they could ever clump into a world. The discoveries surprised almost everyone. The Kepler Space Telescope, watching for the tiny dimming of stars as planets passed in front of them, began to spot these double-sun worlds one by one. Some were gas giants. Some were closer to the size of Neptune. Each one raised the same quiet puzzle. How did they manage to come together in such a turbulent place? One idea is that these planets formed much farther out, in calmer regions of the disk, and then slowly drifted inward to the orbits we see today. Another idea suggests they really did form close in, and that the gas and dust were not as disturbed as the early models predicted. Both views have support. Neither has one. The question of how a planet survives the gravitational tug of two parent stars is still very much open. The skies on these worlds, if you could stand on one, would be unlike anything in our own sky. The two suns would not always rise together. Sometimes one would lead, the other trailing behind by hours. Sometimes the smaller star would slip behind the larger, and the light would dim and shift color in slow, sweeping rhythms. Eclipses would not be rare events. They would be part of the ordinary week. The strangeness does not stop with 2 stars. Some systems hold 3. A few hold 4. There is a world known to circle 1 star in a system where 3 other stars orbit each other nearby. From its surface, you would see a bright primary sun in the sky, and then, far across the dark, 3 more points of light so brilliant they would outshine every planet and moon in the local night. The shadows on such a world would be layered, soft-edged, and always shifting. It is fair to wonder how certain we are about all of this. The signals from these multi-star systems are tangled. Each star contributes its own brightness, its own small wobble, its own gravitational pull. Pulling a planet's signature out of that noise is delicate work. Some claimed planets in tight binary systems have been challenged later, with new data suggesting the dip in light came from the stars themselves, not from a world passing in front. Other candidates have held up well across many years of observation. Sorting the real planets from the ghosts in the data is part of what makes this field so cautious and so slow. The neighbors of strange planets are not always other planets or other stars. Sometimes they are belts of icy debris or thick rings of dust or dim companion, objects too small to be stars, but too large to be planets in any ordinary sense. Brown dwarfs, as these in-between bodies are called, can warm a nearby world with a deep red glow that never quite becomes daylight. A planet circling a brown dwarf would live in a perpetual twilight, lit by something that is neither sun nor moon. What ties all of this together is the simple truth that planets do not exist in isolation. Their orbits, their atmospheres, even their chances of holding onto liquid water depend on what surrounds them. A second star can stabilize a planet's path, or it can slowly pull that path apart over millions of years. A passing companion can scatter worlds into wild, looping orbits. A nearby cloud of debris can rain down for ages, scarring a surface that might otherwise have been calm. So when we look at the strangest planets, we are also looking at the strangest neighborhoods. The dance of bodies around them shapes the worlds we see, and shapes the worlds we have not yet found. Whether each of these double-sunned planets is exactly what we think it is remains. For now, a quiet and unfinished question, drifting in the data, waiting for sharper eyes. Among all the strange planets we have found, the strangest may be the ones that should not exist at all. They orbit the burned-out cores of dead stars. They sit so close to violence that nothing tender should survive there. And yet, somehow, they are the very first planets we ever found beyond our own sun. Picture a star that has already ended. It lived a bright life, then collapsed in a great burst of light called a supernova. What it left behind is not a star anymore. It is a tiny city-sized ball of crushed matter, spinning hundreds of times each second. We call it a pulsar because as it spins, it sweeps a beam of radio waves across the sky, like a lighthouse made of dead starlight. The pulses are so steady you could set your clock by them. In the early 1990s, two scientists noticed something odd in those steady pulses. The beats from one pulsar, named PSRB 1257 plus 12, were slightly off. Not random, not noisy. The timing wobbled in a pattern, as if something was tugging on the pulsar from outside. The simplest answer was almost impossible to believe. Planets, at least two of them, and later a third, smaller one. Tiny worlds circling the corpse of a star. These were the first confirmed planets ever found outside our own solar system. Not warm Earth-like worlds, not soft blue oceans. The first planets we ever discovered were ghosts orbiting a ghost. Now think about what it must be like there. The pulsar is barely the size of a city, but heavier than the sun. Its gravity is fierce. Its rotation is dizzying. From the surface of one of these planets, you would not see a sun in the sky. You would see a dim point of dead light, washed in radio waves and X-rays. The ground would be bathed in a steady, invisible storm of radiation. No soft dawn, no gentle dusk, just the sweep of that lighthouse beam again and again, faster than a heartbeat. How did these planets even get there? That is one of the deepest puzzles in all of exoplanet science. A supernova is a violent ending. It should have torn any nearby planet apart or flung it away into the dark forever. So either these worlds survived the death of their star, somehow shielded or lucky, or they formed afterward, built from the debris that fell back around the pulsar. Some researchers favor the second idea. They picture a disk of shattered matter slowly cooling around the corpse, gathering itself into small rocky bodies, the way our own planets once did around the young sun. Others wonder if the pulsar captured wandering objects later, pulling them into orbit by chance. The question remains open. A few years after PSR B 1257 plus 12, astronomers found something even stranger. A pulsar with a planet so old it nearly breaks the heart. The world, sometimes called Methuselah, is thought to be around 12.5 billion years old. That is almost as old as the universe itself. It would have formed when galaxies were young and the cosmos was still finding its shape. If the age estimate is right, this planet has been quietly orbiting for nearly the entire history of everything. One possibility is that planets are far older and more common than we ever imagined. Another possibility is that the age estimate is wrong, tangled in the difficulty of dating such distant systems. The evidence is incomplete. What does a planet do for 12 billion years around a dead star? We do not know. It may be frozen solid. It may be slowly grinding down under tidal forces. It may have changed orbits many times as its system shifted. From our distance, all we can read are tiny ripples in the pulsar's beat. The rest is left to imagination. There is something tender about these pulsar worlds, in spite of the harshness. They sit at the very edge of what we thought a planet could be. They were found by listening, not by looking, by counting the soft tick of a dead star's radio pulse. And they remind us that the universe builds quietly even in the ruins. Where one star ended, small worlds gathered. Whether they were survivors or newborns, they are there now, turning slowly in the dark. Some astronomers caution that not every claimed pulsar planet has held up under closer study. Timing signals can be fooled by stellar quakes, by clouds of charged particles, by patterns we do not yet fully understand. A few candidate pulsar worlds have quietly faded from the catalogs. Others remain firm. Which are real and which are echoes of noisy data is still being worked out. slowly, beat by patient beat. Far from us, on worlds we will never visit, there are skies that behave in ways our own sky never has. On some of these planets, the clouds are not made of water. They are made of metal. Tiny droplets of iron, vaporized on one side of the world and carried by hot winds, may cool just enough on the other side to fall as rain. Soft, slow, glowing rain, hot enough to melt almost anything it touched. The world most often linked to this idea is a hot Jupiter studied with great care by space telescopes. Its day side burns at temperatures hot enough to vaporize iron. Its night side, while still very warm, is cool enough that some of that iron may condense back into droplets. Strong winds carry the vapor from the bright side to the dark side, where in theory it falls. That is the picture many researchers favor. Other scientists point out that the signal in the data could be explained in different ways, perhaps by other metals or by chemistry we have not yet pinned down. The rain may be real. It may also be a story we tell to fit a faint whisper of light. Even if iron rain is real on that one world, the details remain soft and uncertain. Are the droplets the size of dust grains, or fat like summer raindrops at home? Does the rain reach the lower atmosphere, or does it evaporate again before it falls far? No one can say. The planet is too far. The light we collect from it is too thin. We can only sketch the broad shape of the weather and wonder about the rest. Other strange worlds may carry clouds of stranger stuff still. Some hot Jupiters seem to have skies laced with silicate clouds, tiny grains of the same minerals that make sand and glass. On those planets, when the wind blows hard enough, the air itself might shimmer like a fine mist of crushed quartz. Closer to certain very hot stars, models suggest clouds of aluminum oxide, the same material used to make sapphires and rubies. If those clouds exist, sunsets there might glow with a soft red or pale blue color, lit by gemstone dust hanging in the upper air. Whether those clouds form sheets or patches or thin veils, we do not know. The colors we imagine are guesses dressed up in math. Some cooler exoplanets, the ones called brown dwarfs that sit between planets and stars, may have clouds of molten salt sodium chloride, the same chemical as the salt on your kitchen table, but hot enough to flow as liquid through the sky. On still cooler worlds, the clouds might be made of sulfides, dim and gray, more like smoke than rain. Each kind of cloud leaves a faint mark on the light we collect. Each mark could mean several different things. One team reads the data one way. Another team reads it another. The clouds themselves stay quiet, far beyond our reach. There are smaller wonders too. On lava worlds, where one side is an ocean of melted rock, scientists think there may be a thin atmosphere of vaporized minerals. Sodium, potassium, silicon monoxide, drifting in a hot, glowing haze. As winds carry that vapor over the cooler night side, tiny grains of rock might condense and fall as a fine stone snow, a snowfall of pebbles, soft and slow under a black sky. That picture is built from models, not from any direct image. Whether the snow is real or only a useful guess is still open. On some giant planets, the deep interior may rain liquid helium through liquid hydrogen, in droplets so small they are more like a mist than rain. On others, the famous idea of diamond rain returns, with carbon squeezed into tiny crystals that fall through layer after layer of pressurized fluid. The droplets, the crystals, the slow descent through dense air. We picture these scenes clearly in our minds, but no probe has ever flown through them. They are weather reports written in pencil, ready to be erased. What ties these quiet details together is how small and gentle they are, even when the materials are extreme. Iron, sapphire, salt, stone, diamond. The fiercest substances we know, falling as soft rain on worlds that may or may not behave the way we have guessed. The strange thing is not only that such weather might exist, it is that we are sitting here on a small blue world trying to read the faint colors of starlight and tell whether a planet hundreds of light years away has metal in its clouds. Some of it is surely real. Some of it is surely wrong. Which is which, we do not yet know. The story of finding planets around other stars is younger than you might guess. For most of human history, the worlds beyond our own sun were only a hope. Ancient astronomers in Babylon, in Greece, courts of medieval Persia, tracked the wandering lights of our own neighborhood with patient care. They built clay tablets and brass instruments. They mapped the slow drift of the night. But the planets they knew were only the handful that orbit our star. For thousands of years, the question of other worlds was a question of philosophy. Thinkers wondered if every star might have its own family of planets, or if our sun was somehow alone. There was no way to look closely enough to find out. Stars are too bright, and planets are too small and too dim. A planet beside a star is like a moth beside a lighthouse, lost in the glare from many trillions of miles away. The first hints came in the early 20th century from astronomers measuring the tiny wobbles of nearby stars. The idea was simple and clever. A planet tugs on its star as the star tugs on the planet. If you could measure the star moving back and forth, even by a hair, you might catch the shadow of a hidden world. For decades, this method gave only false alarms. Stars that seemed to wobble turned out to be quiet. Stars that seemed quiet turned out to wobble in ways no one could explain. Then, in 1992, something strange happened. Two astronomers working at a giant radio telescope in Puerto Rico were studying a pulsar, the spinning corpse of a dead star. Pulsars send out pulses of radio light with the steady rhythm of a cosmic clock. By listening to tiny stumbles in that rhythm, the astronomers realized that small worlds were tugging on the pulsar from nearby orbits. These were the first confirmed planets outside our solar system, and they were astonishing. They circled a star that had already died. This discovery raised more questions than it answered. How could planets exist around such a violent, ancient object? Were they survivors of the supernova that made the pulsar? Were they born again from the wreckage in a second generation of planet making? Both ideas remain on the table. The pulsar planets are old, far older than Earth, and the story of how they came to be is still not fully written. 3 years later came the next great moment. In 1995, 2 Swiss astronomers announced a planet orbiting a sun-like star called 51 Pegasi. They had used the wobble method, refined over many patient years, on a quiet star 50 light years away. The the world they found was nothing like anyone expected. It was a giant planet, larger than Jupiter, hugging its star in an orbit of only 4 days. No theory of planet making had predicted such a thing. The discovery shook the field. After 51 Pegasi, the floodgates opened slowly. New instruments were built. Telescopes on mountain tops measured starlight with finer and finer precision. Then came the transit method, where astronomers watched for the faint dimming of a star as a planet passed in front of it. The dimming is tiny, often less than a single %. To catch it, you need patience and very steady eyes. In the 2000s, a space telescope called Kepler was launched to stare at one patch of sky for years on end, watching for these small shadows. Kepler found thousands of candidate worlds. Some were rocky, some were giant, some were oddly puffy, some seemed not to fit any category at all. With every new world, the strangeness deepened. Astronomers learned that planet making is far more varied than our own solar system suggested. They also learned how easy it is to be fooled. A faint dimming can come from a passing planet, but it can also come from a background star, or a flare, or noise in the data. That is the quiet shadow over the whole history. Many of the strangest worlds in the catalog rest on signals that are real but faint. Some early announcements have been quietly withdrawn over the years as better data washed them away. Others have grown stronger with time, surviving every test. We are still in the early days of sorting, which strange planets are truly strange, and which are illusions born of difficult measurements. What this history shows is how recent our knowledge is. The first true confirmation of a planet beyond our solar system came less than half a lifetime ago. The instruments are still maturing. The methods are still being refined. And the worlds we have already found, ancient and unexpected, are only the first whispers of what may be waiting in the dark. Most of us picture a planet as a sphere, a simple round ball, smooth and balanced, turning slowly in the dark. That picture is mostly right, but not always. Out among the strangest worlds we have found, some planets seem to break the rule of roundness itself. They stretch, they bulge, they lean, they wobble in ways that hint at forces we are still learning to measure. Consider a world called WASP 103b. It orbits its star so closely that a full year there lasts less than a single Earth day. At that distance, the star's gravity pulls on the planet from one side, while the planet's own gravity tries to hold itself together. The result, according to one set of measurements, is a planet shaped less like a ball and more like a rugby ball. A gentle egg drawn out along the line between itself and its sun. The data came from a sensitive space telescope watching the planet pass in front of its star. The shape of the dip in starlight, when measured carefully, seemed to match a slightly stretched world rather than a round one. If that reading is correct, it would be the first time we have ever measured the actual shape of a planet outside our solar system. A quiet, remarkable first. The honest answer is that we are not yet sure. Other astronomers have looked at the same data and pointed out that the signal is faint. The stretching, if real, is small. It could be hiding inside the noise of the instruments or inside our assumptions about the star. Several teams are still going back and forth, gently arguing about whether the egg shape is truly there. The mystery sits open, waiting for better measurements. Even our own planets give us hints that perfect roundness is rare. Saturn bulges noticeably at its middle because it spins so quickly. Jupiter does the same. Earth, too, is a little wider at the equator than from pole to pole, though only by a small amount. So the idea that a close-in gas giant could be stretched by its star is not strange in principle. The strangeness lies in trying to see it from many light years away. Other planets seem lopsided in different ways. Some hot Jupiters appear to have one side that is brighter, hotter, or cloudier than the other. Even after accounting for the fact that they always show the same face to their star. The bright spot, in some cases, does not sit directly under the star as you might expect. It drifts off to one side, as if blown by enormous winds in the upper atmosphere. Why those winds blow the way they do, and why the offset is larger for some planets than others, remains a quiet puzzle. There are also worlds where the heat seems strangely uneven, for reasons no one fully understands. One side glows brighter than models predict. The other side stays cooler than it should. Some researchers wonder if thick clouds on the night side are trapping heat in unexpected ways. Others suggest the planet's magnetic field might be steering the flow of charged gas, smearing warmth around like cream stirred into coffee. Both ideas fit some of the data. Neither explains all of it. And then there are the rings. We have only one confirmed candidate for a ringed exoplanet, and even that one is debated. A young object called J1407b once produced a long, complex dip in the light of its parent star, lasting weeks. The pattern hinted at a vast ring system, possibly far larger than Saturn's. Some researchers think it really was a giant set of rings around a young planet. Others suspect it might have been a disk of dust forming moons, or even a binary companion of some kind. We have not seen another dimming like it since. It is worth sitting for a moment with how strange this all is. We are trying to measure the shape of objects we cannot see directly. We are inferring stretched bodies, drifting hot spots, uneven hemispheres, and possible rings from tiny flickers of starlight crossing trillions of miles of empty space. Every measurement carries some uncertainty. Every uncertainty leaves room for surprise. Maybe WASP 103b really is shaped like a soft egg, pulled gently by its star. Maybe the lopsided glow of certain hot Jupiters comes from winds we have not yet understood. Maybe J1407b once wore rings broader than any in our own neighborhood. Or maybe some of these strange shapes will quietly dissolve as our instruments grow sharper, replaced by rounder, calmer worlds. We do not yet know which surprises will survive. For tonight, it is enough to picture them turning slowly in the dark, a little stranger than spheres, waiting to be seen more clearly. When we picture a planet, most of us imagine something tidy, a round world circling its star in a calm, steady ring. The orbit is gentle. The path is patient. Year after year, the planet returns to roughly the same place, like a marble rolling along a smooth groove. Our own solar system is mostly like this. The planets follow nearly circular paths, all tilted in roughly the same flat plane, all moving in the same direction. It feels like the natural order of things. The wider galaxy seems to disagree. Out among the distant stars, astronomers keep finding planets on orbits that make very little sense at first glance. Some swing close to their stars in tight, narrow loops, then race far out into the cold, then come tearing back. These stretched paths are called eccentric orbits, meaning oval instead of round. A few exoplanets follow paths so elongated they almost resemble the orbits of comets. The planet bakes for a short, brutal stretch, then drifts through long, frozen darkness, then bakes again. How does a planet end up on a path like that? One idea is that these worlds were not always so restless. They may have formed peacefully in calm, circular orbits, and then been shoved by the gravity of a neighbor. Picture two large planets born side by side, gently tugging on each other across millions of years. Eventually, one tug becomes too much. One planet is flung inward, the other outward, and a once quiet system becomes a place of long, looping chaos. Some researchers wonder whether our own solar system passed through a quieter version of this same shuffling long ago. Another idea points to passing stars. The galaxy is full of motion, and stars sometimes drift close enough to disturb a planetary family from outside. A nudge from a stranger, lasting only a few thousand years, could leave behind orbits that look bent and bruised for billions of years afterward. Stranger still are the planets that orbit backward. In most systems, the planet circles in the same direction the star spins. It is the leftover spin of the cloud they were both born from. But a handful of hot Jupiters, gas giants nestled scorchingly close to their stars, appear to travel the wrong way around. They run against their star's rotation, like a single swimmer pushing upstream, while the river flows the other way. No one is fully certain how this happens. One theory blames a slow gravitational dance with a distant companion, a process that tips a planet's orbit further and further until it flips entirely. A competing theory suggests violent scattering early in the system's life, where a near collision sent one survivor tumbling into a reversed path. The evidence is not yet enough to choose between them. Then there are the planets on tilted orbits, Instead of moving along the flat plane of their star's equator, they ride high above or low below it, as if a child had taken a model of the solar system and bent one ring sideways. Some tilts are small, some are extreme, almost vertical. These tilted paths hint that early planetary systems may be far rougher places than our own quiet sky suggests. The mystery deepens when planets share their orbits in unusual ways. In a few systems, two planets seem locked together by gravity, taking turns approaching the star, trading energy back and forth in a slow, steady rhythm. These are called resonant orbits, where the timing of each planet's year matches the others in simple ratios. 2 trips for 1, 3 trips for 2. Are these tidy patterns common across the galaxy? Or are they rare survivors of long-ago chaos? The answer is still forming. And some of these strange orbits may not be real at all. A wobble in starlight can be caused by a planet on an odd path, or by spots on the star itself, or by noise in the instrument. Astronomers sometimes announce a strange orbit, only for later data to soften the claim. A planet thought to swing wildly may turn out to swing gently, or it may vanish entirely, revealed as a ghost in the data. The question of which strange orbits are genuine and which are illusions of noisy starlight remains very much alive. What ties all of this together is connection. No planet drifts in isolation. Each one feels the pull of its siblings, its star, and sometimes the distant whisper of stars passing by. Their orbits are letters written in gravity, slowly composed across billions of years. Reading those letters is hard. The handwriting is faint. The ink fades into the noise of the cosmos. And so, the planets keep tracing their odd, patient loops, and we keep watching, still unsure how much of what we see is the truth of their motion. Somewhere far from here, a world may be drifting slowly around its star, wrapped in an ocean deeper than any sea on Earth. We do not know for certain that such places exist. We only know that some of the planets we have found behave as if they might be made mostly of water, and that idea has been shifting and reshaping itself for years. The story of these possible water worlds is a story of slow change, 50 years ago, almost no one talked seriously about ocean planets. The first exoplanets we noticed were giants, hot and heavy, easy to spot because they pulled hard on their stars. Smaller worlds stayed hidden as our tools grew gentler and more patient. A new kind of world began to surface in the data. These planets were larger than Earth, but smaller than Neptune. Their weight, measured against their size, suggested they could not be solid rock. Something lighter had to fill them. Water became one of the leading guesses. A name slowly emerged for some of these candidates. Researchers began calling them Hycean worlds, a soft blend of the words hydrogen and ocean. The idea is gentle and strange. A deep, warm sea covers the entire planet. Above it, a thick blanket of hydrogen gas reaches into the sky. No continents, no shores, just water below, and a heavy, quiet atmosphere above, glowing faintly in the light of a small red sun. Not everyone agrees that these worlds are oceans at all. The same measurements could fit a planet wrapped in a thick steam atmosphere with no real liquid surface, or a world where water and rock blend together under crushing pressure into something that is neither fully sea nor fully stone. Some researchers wonder if the surface could be a slow, syrupy layer, warm and dense, more like hot glass than open water. The numbers we have do not yet pick a winner. Each theory holds part of the data, and each leaves part unexplained. What makes this so interesting is how the picture keeps changing. A planet that looked like a likely ocean world one year may look like a steam world the next. Once new readings come in, telescopes in space have begun to taste the air of some of these distant planets by watching starlight pass through their atmospheres. Different gases bend the light in different ways. A hint of water vapor here, a whisper of methane there. Sometimes the signal is strong. Sometimes it fades when other groups try to measure it again. The mystery moves like a tide, advancing and pulling back. There is also the question of time. Even if an ocean does exist on one of these worlds today, it may not last. A planet so close to its star can lose its water slowly, molecule by molecule, as starlight strips the upper air away. Over millions of years, A deep sea could thin into a shallow one, and a shallow one could vanish into space. Other worlds may be moving in the opposite direction, gathering water as icy bodies crash down from the outer edges of their systems. We are looking at single frames of very long stories, and we do not always know which way the story is going. Closer to home, our own ideas about water in the universe have shifted too. Once, liquid water seemed rare and precious, a gift Earth alone enjoyed. Now, we suspect oceans beneath the icy crusts of small moons in our own neighborhood. If water hides under the shells of frozen moons here, it becomes easier to imagine vast open seas on planets we cannot yet visit. The definition of an ocean world keeps softening and stretching to fit what we find. Still, the central question remains open. We do not know how many of the possible water worlds are truly watery. We do not know if the warm Hycean planets are calm blue spheres or boiling pressure cookers. We do not know whether life, if it ever begins in such places, would find that endless sea comforting or strange. Our instruments are getting better each year, and the answers will keep shifting as they do. A world that seems certain tonight may look entirely different in a decade. For now, picture it gently. A planet wrapped in a sea with no shore. Slow, dark currents moving through water that has never known a beach. A sky thick and pale, holding the warmth in. Somewhere in that long, patient ocean, perhaps nothing stirs. Perhaps something does. The story is still being written in the quiet space between one measurement and the next, and we are only beginning to listen. Light is how we find these worlds. We almost never see a planet directly. We see the light of its star, and we watch how that light changes when a planet passes in front. From those tiny dips and shifts, astronomers can read the chemistry of a sky we will never visit. And sometimes, when the light tells its story, the story is that the sky itself is leaving. There are planets out there whose atmospheres are boiling away into space. They orbit so close to their stars that the upper layers of their air get heated past the point of holding on. Hydrogen, the lightest gas, climbs up and slips free. Helium follows. Heavier molecules linger longer, but they too begin to rise and drift. From far away, through a telescope, We see this as a faint, glowing tail behind the planet, like the slow exhale of a candle in still air. The first hints came when astronomers studied a hot Jupiter that passes in front of its star every few days. When they looked at the star's ultraviolet light during the crossing, the dip was far deeper than the planet alone could explain. Something larger than the planet was blocking the light. That something seemed to be a cloud of hydrogen streaming away into the dark. The planet looked like a comet, with a vast, invisible plume trailing behind it. We could not see the gas with our eyes, but in ultraviolet, it shimmered into view. Other planets show the same gentle bleeding. A few have been caught losing helium, which glows in a specific shade of infrared light. The helium signal arrives like a soft whisper, telling us that high above the cloud tops, gas is escaping faster than gravity can hold it. Some of these worlds may lose a noticeable fraction of their mass over billions of years. Others may have already lost most of what they once had, leaving behind only a hot, heavy core. This raises a quiet question. How much air can a planet lose before it becomes a different kind of world altogether? One idea is that some of the small, dense planets we see today began life as much larger gas worlds, then had their atmospheres stripped away by the heat of their stars. A second idea is that they were born small and rocky and never had thick air to begin with. The light cannot yet tell us which story is true. Both fit the data. Both leave parts of the picture missing. The colors of these escaping atmospheres are strange to imagine. In ultraviolet, the hydrogen tail glows in a shade no human eye can see. A deep electric tone past violet. The helium signal hides in the near infrared, just beyond red. In light, we feel only as warmth. If you could stand on a moon of one of these planets, the sky above the doomed world might look pale and washed out. The colors faded by constant stellar wind. The star itself would loom huge and white, its light pressing down on the thinning air like a hand on a soap bubble. There is debate about how fast this loss really happens. Some models predict slow, steady escape over billions of years, gentle enough that the planet keeps most of its weight. Other models suggest sudden bursts, when the star flares and tears off great sheets of upper atmosphere in a single afternoon. The truth almost certainly lies somewhere between, and probably differs from planet to planet. We are still learning to read these signals. There is also the question of whether what we see is really atmosphere at all. A faint extra dip in ultraviolet light could be gas escaping a planet. It could also be a cloud of dust between us and the star, or a flicker in the star's own behavior, or an instrument quirk we have not yet understood. When the signal is small, the interpretation is fragile. More than once, an exciting claim of atmospheric loss has softened on closer inspection. The light is honest, but it is also faint, and faint light is easy to misread. Still, the pattern across many planets is real. Air is leaving worlds. Somewhere out there, right now, a hot blue giant is shedding hydrogen into the void. A long, pale streamer fanning out behind it, lit from one side by its star and lost on the other side to endless dark. We will never feel that wind. We only see its shadow in light that took hundreds of years to reach us. And we sit with the gentle question of what those worlds were before the air began to leave, and what they will be when the last of it is gone. If you could press your ear against the cosmos and listen for the sizes of planets, you would hear something strange. A great hum of small worlds, a steady chord of larger ones, and in between, a quiet gap, a missing note. Astronomers have been studying this gap for years, and they still are not sure what it means. The gap has a name. It is called the Radius Valley. When researchers count the planets they have found and sort them by size, two clear groups appear. There are many small rocky worlds, a little bigger than Earth. There are many puffier worlds, closer in size to Neptune. But planets in the middle range, roughly 1.5 to 2 times the width of Earth, show up far less often. The numbers dip. The chord goes quiet. For a topic about sound, this is the strangest one of all. It is the sound of absence, the hush between two crowded notes. What could carve out such a gap? One idea points to the stars themselves. Young stars are loud, in a way. They pour out high-energy light and a fierce stellar wind. a steady stream of charged particles. A young planet sitting close to its star feels this wind like a constant gale. If the planet is small and only lightly wrapped in gas, the wind can strip that gas away. Over millions of years, a Neptune-sized world could shrink down into a bare rocky core. The middle sizes vanish because they do not last. They erode into the smaller group below. A competing idea points inward instead of outward. In this theory, the planet itself supplies the heat. After a rocky world forms, its hot interior slowly leaks energy upward through its atmosphere. That gentle warmth, working from below over 1 billion years, can puff a thin gas layer back into space. The result looks similar from the outside. Middle-sized planets become rare, but the mechanism is different. One blows the atmosphere off from above. The other lets it drift away from beneath. Both ideas might be partly right. Both might be partly wrong. The data does not yet decide between them. There is also a quieter possibility, one that has nothing to do with planets at all. It is the possibility that the gap is a trick of our instruments. The methods we use to find exoplanets are not equally sensitive to every size. A planet that crosses in front of its star, dimming the light a little, is easier to see when it is large. A small planet barely registers. A middle-sized planet sits in an awkward range where some detections succeed and others fail. If our nets have holes shaped like a certain size, of course that size will seem missing. Most researchers think the gap is real. The statistics have been carefully corrected for these blind spots, and the dip still appears. But the lingering doubt is part of what makes the question interesting. We are listening to a faint silence in a very noisy sky, and we have to ask whether the silence belongs to nature or to us. There is something soothing in this idea, even the most patient counting, even the most careful sorting of thousands of worlds, still leaves room for wonder. The galaxy may be hiding a hidden chorus of middle-sized planets that our telescopes simply cannot hear well. Or those worlds may have truly been silenced long ago, their atmospheres carried off into the dark, leaving only the smaller and larger voices behind. You can picture the scene if you like. A young star, blazing white hot in its first 100 million years. A close-in planet wrapped in a hazy blue envelope of hydrogen. A slow, invisible wind peeling the envelope away in long streamers, like mist lifting off a lake at dawn. After enough time, only a dark rocky ball remains, smaller than it once was, turning quietly in the star's glare. Multiply this scene by billions across the galaxy, across billions of years, and you begin to sense why a whole-size class might thin out. Or picture a different scene. The same planet, but the wind is gentler than we thought. The atmosphere stays. The world becomes one of those mid-sized Neptunes after all. Somewhere out there, in a system we have not yet examined closely. This version might be the common one. The honest answer is that we cannot yet say which picture rules the galaxy. Both could be true in different places. Neither may be the full story. For tonight, it is enough to listen to that soft gap in the planetary census, that missing middle note, and let it remind you how much of the cosmic song we are still learning to hear. Some planets do not merely orbit their stars. They crumble as they go, leaving long trails of dust behind them, like comets made of melting rock. And the strange thing about these crumbling worlds is that we can describe them with numbers so clean, so simple, that the math itself feels almost like music. Think of a small rocky planet drifting so close to its star that a single year, one full trip around, takes only a handful of hours. The orbit is tight. The star looms huge in its sky. And because the planet sits so near to that furnace, its surface boils away into space. Each pass strips a little more material into a glowing tail. The math behind that orbit, though, is the same math that describes a stone tied to a string. The stone swings faster when the string is shorter. A planet swings faster when its orbit is smaller. The same rule, the same simple ratio. This idea goes back about 400 years to the quiet realization that the square of a planet's year is tied to the cube of its distance. Two numbers lifted to small powers, locked together for every world that has ever existed. Mercury obeys it. Earth obeys it. A crumbling planet 30 light years away, with a dust tail streaming behind it, obeys it too. The same equation that lets us predict a sunrise also predicts when a disintegrating world will pass between us and its star. When that passage happens, the star dims by a tiny amount, not by much, often less than 1 part in 1,000. But the dip has a shape, and the shape carries information. A solid round planet makes a clean, symmetric dip. A crumbling planet, trailing dust, makes a lopsided dip with a long, slow tail on one side. Astronomers can read that asymmetry the way a sailor reads a wake. The math turns a tiny shadow into a portrait of something falling apart. A few of these strange worlds have already shown themselves this way. One circles its star in less than 10 hours. Another seems to be losing roughly a moon's worth of mass every billion years, which sounds slow until you remember that nothing is replacing it. The numbers say these planets cannot last forever. The same equations that describe their orbits also describe their endings. What remains open is the question of what these worlds actually are underneath the dust. Some researchers wonder if they began as small rocky planets, only slightly bigger than Mercury, that drifted inward over time. Others suggest they might be the exposed cores of larger worlds, whose outer layers were stripped away long ago. A third idea is stranger still, that the dust tail itself is not coming from a planet at all, but from a swarm of small bodies orbiting together, fooling our instruments into seeing a single object. The light curves are noisy. The signal is faint. The competing pictures all fit the data, and none of them fits perfectly. The elegance lies in how few numbers we need to even start asking. An orbital period, a transit depth, a stellar mass. From those 3 measurements, and a handful of constants that have not changed since the universe was young, we can sketch the size of a world, the temperature at its surface, the speed of its falling material. The universe seems content to run on a small handful of rules, applied over and over at every scale. The same gravity that holds your feet to the floor shapes the tail of a vaporizing planet 30 light years from here. There is something soothing in that. A crumbling world sounds chaotic. A trail of dust sounds messy. But the trajectory of every grain in that tail detail follows the same quiet equations that describe a pendulum, a tossed ball, a moon in slow circles around its mother world. Even disintegration has a rhythm. Even loss can be predicted to the second. What we cannot yet predict is how common these vanishing planets are. A few have been confirmed. Many more may be hiding in data we have already collected, their signals too faint to separate from instrument noise. The mathematics is ready. The observations are still catching up. Whether the galaxy holds a handful of these crumbling worlds or thousands remains an open question waiting on better telescopes and patient eyes. For now, picture one of them. A small dark shape against a bright star, with a soft veil of dust trailing behind, glowing faintly where the starlight catches it. The orbit closes. The shadow passes. The numbers, unchanged for billions of years, keep their quiet promise. And somewhere in that simple arithmetic, a world is gently coming undone. Step away from the planets for a moment and think about their moons. Some of the strangest worlds we know of are not planets at all. They are the small bodies that circle larger ones, tucked into the gravity of a parent world. In our own solar system, a few of these moons hold mysteries that may run deeper than anything we have found around distant stars. Consider the icy moons of the outer planets. Beneath their frozen shells, several of them likely hide oceans of liquid water. One of them, a small moon of Saturn, sprays plumes of salty water out into space through cracks in its surface. The fact that liquid water exists at all, so far from the warmth of the sun, depends on a delicate balance. The moon is squeezed and stretched by the gravity of its parent planet as it orbits. That squeezing creates heat deep inside. Without that constant flexing, the ocean would freeze solid. Change the orbit slightly, and the warmth vanishes. This is what makes these worlds so fragile to think about. A small shift in distance, a small shift in shape, and the balance would tip. Some researchers wonder whether similar moons might orbit giant planets around other stars. These would be called exomoons, and so far no one has confirmed one with certainty. A few candidates have been suggested, but the signals are faint, and the data leaves room for doubt. the question of whether exomoons are common, rare, or hiding in plain sight remains open. If they are common, the implications are quietly enormous. A gas giant in the habitable zone of its star could carry several moons along with it. Each of those moons might have its own atmosphere, its own surface, its own slow weather. Some researchers wonder if the most life-friendly places in the galaxy might not be planets at all, but moons. Others point out that moons face their own challenges. Strong radiation from the parent planet, tidal stresses, and unstable orbits could all make life difficult. The truth likely depends on details we cannot yet measure. Closer to home, the largest moon of Saturn carries an atmosphere thicker than our own. Lakes of liquid methane and ethane sit on its surface, fed by a slow rain of hydrocarbons from orange skies. The temperature is far too cold for water to flow. Yet rivers still carve channels through the icy ground. It is a world that looks almost familiar from a distance and almost completely alien up close. Whether anything chemical and self-sustaining could exist in those cold lakes is an open question. Some researchers have proposed exotic forms of chemistry that might work there. Others doubt that the cold allows for the kinds of reactions life would need. The evidence is incomplete. The fragile balance shows up everywhere you look. A moon that is slightly too small loses its atmosphere to space. A moon that is slightly too far from its planet stops being warmed by tides. A moon that drifts too close gets pulled apart by gravity into a ring of rubble. The fact that any moon holds onto an ocean, or an atmosphere, or a stable surface depends on a long list of conditions, all happening to line up. The same is true for Earth. Our world sits at just the right distance from the sun to keep water liquid across most of its surface. Our atmosphere is thin compared to the planet beneath it. Yet, it holds in enough warmth to keep us from freezing and blocks enough radiation to keep us alive. Our large moon stabilizes the tilt of our axis, which keeps the seasons from swinging wildly. Move any of these dials a small amount, and the picture changes. Some researchers wonder how unusual this arrangement really is. Others suspect that something like Earth, in broad outline, might be common? The honest answer is that we do not yet know. When you set the strangest planets next to the strangest moons, the contrast is striking. Planets dominate the conversation because they are easier to find. But moons may be where some of the most interesting chemistry quietly unfolds, hidden under ice or veiled in thick orange haze. We have only begun to look for moons beyond our solar system, and the techniques to do so are still young. For now, the question of where the strangest worlds really live, on planets or on the small companions that circle them, stays open. Tonight it is enough to picture a small moon, glowing faintly in the reflected light of its giant parent, holding a dark ocean under a sheet of ice. Quiet, patient, and barely understood. Drift with that image for a while. Among all the strange worlds we have found, one kind keeps slipping through our fingers. A mirror Earth, a planet about the size of our own, made of rock and metal, orbiting a sun-like star at just the right distance for water to pool on its surface. We have not found one yet, not for certain. And the reasons we have not found one tell us a great deal about how little we can still see. The problem is not that mirror Earths are rare. The problem is that they are small, and they are dim, and they hide in the glare of their stars. A true Earth twin would cross the face of its star and dim its light by less than 1 part in 10,000. That tiny dip is right at the edge of what our best space telescopes can detect. A passing cloud of star spots, a flicker in the instrument, a stray cosmic ray. All of these can create false signals that look just like a small rocky world. So when a promising candidate appears, the question that follows is always the same. Is this a planet? Or is this noise pretending to be a planet? Some early candidates from years past have quietly faded as better data came in. Others have grown stronger. A few sit in a strange middle place, neither confirmed nor ruled out, waiting for a future instrument to settle their case. There is also the puzzle of what we even mean by a mirror Earth. One school of thought says the size and orbit are what matter most. If a world is roughly Earth-sized and sits in the habitable zone, the band around a star where liquid water could survive, then it counts. By that definition, several candidates already exist, but another view holds that size and orbit are only the surface of the question. The real test is the atmosphere. Without knowing what gases surround a planet, we cannot say whether its surface is mild or scorching or frozen solid. This is where our limits show themselves clearly. We can measure the size of a small planet sometimes. We can estimate its mass sometimes. But peering into the air of an Earth-sized world around a sun-like star is, for now, beyond what we can do. The signal is simply too faint. Larger planets around smaller, dimmer stars give us better odds, which is why so much attention has turned to red dwarf systems. Worlds like the ones around the nearby star TRAPPIST-1 are easier to study because the star is small and the dimming is deeper. Yet, red dwarf worlds may not be true mirrors of Earth. Their stars flare often, bathing nearby planets in bursts of radiation. Tidal locking is likely, with one side always facing the star and the other locked in endless night. Some researchers think life could still arise in such places, perhaps along the twilight ring between the two halves. Others suspect that the constant flares would strip away atmospheres long before life had a chance. The debate is genuine, and the evidence is thin on both sides. A real Earth twin around a real Sun twin remains the quiet prize. Several missions in planning aim for exactly this target. The hope is to build telescopes large enough and shielded enough to block out a star's light and reveal the faint glow of a small planet beside it. If that works, we might one day read the colors of its atmosphere and guess at the chemistry of its surface. We might see hints of oxygen or methane or water vapor. We might see nothing recognizable at all. There is a deeper uncertainty woven through all of this. We have only one example of a living world, our own. We do not know if Earth is typical or strange. The whole search assumes that life prefers conditions much like ours. But that assumption could be wrong. A mirror Earth might be lifeless. A world that looks nothing like Earth might be teeming. We are searching with a single map, and we do not know how accurate the map is. So the question lingers, soft and patient. How many true Earth twins exist within reach of our telescopes? Are some of the candidates already in our catalogs the real thing, waiting only for better instruments to confirm them? Or will the first confirmed mirror Earth turn out to be something we have not yet noticed at all, hidden in a corner of the sky we have barely looked at? For now, we sit with the uncertainty. The data is noisy. The signals are small. The galaxy is wide and patient, and we are just beginning to learn how to listen. Most of the planets we have found do not announce themselves with light. They reveal themselves by shadow. When a distant world passes between us and its star, the starlight dims by a tiny fraction, and that small dimming is often the only sign that the planet exists. We have never seen its surface. We have never seen its color. We only know that something dark passed in front of something bright, and from that flicker, we have built a whole catalog of strange worlds. This is a humbling way to know a thing. It means our maps of the galaxy are full of shadows we have learned to read, and full of shadows we have not yet learned to notice. A planet whose orbit never carries it between us and its star will leave no dimming at all. A planet too small or too far from its star may dim the light by less than our instruments can measure. The galaxy could be crowded with worlds we have simply never seen. In 1,000,000 years, our descendants, if they are still curious, still listening, may look back at our current catalog the way we look back at the first crude maps of the oceans. Our lists of strange planets will seem charming, partial, and full of guesses. The diamond worlds may turn out to be something else entirely. The puffed giants may have shrunk and cooled. The lava hemispheres may have crusted over into dark, glassy plains. Planets, like everything else, do not sit still. In 1,000,000,000 years, the sun will have grown hotter and wider, and many of the worlds we know best will have changed beyond recognition. Mercury and Venus will likely have been swallowed. Earth's oceans will have boiled away. Mars may briefly become warmer before it, too, is scorched. The strange planets in other systems will be on their own slow paths. Some hot Jupiters will have spiraled into their stars and vanished. Some lonely wanderers drifting between the suns will have cooled toward the temperature of deep space, their atmospheres frozen onto their surfaces in pale layers of ice. new worlds will be forming all the while. In the dusty disks around young stars, gravity will be pulling pebbles into boulders, and boulders into small planets, and small planets into giants. Some of these new worlds will be stranger than anything in our current catalog. There will be hot Neptunes we have no name for, and ocean worlds we have not yet imagined, and rocky planets with skies of chemistries we cannot guess. The galaxy is not finished making planets. It is still in the middle of the work, which means the question of what is real and what is noise will never quite close. Each generation of telescopes will catch shadows the last one missed. Each new method will reveal a class of planets that was hiding in plain sight. The superpuffs were hiding in plain sight until recently. The disintegrating planets were hiding in plain sight. The free-floating wanderers were almost certainly hiding for a very long time, and may still be hiding by the billions. Some of the strange worlds in today's catalog will, in time, be confirmed in beautiful detail. We will learn the colors of their clouds, the shapes of their continents, if they have any, the rhythms of their weather. Others will quietly fade from the lists as better data shows the original signal was something else. A star spot, a flicker in the instrument, a second star too faint to see. Both outcomes are part of the same slow process. Astronomy corrects itself patiently across lifetimes. 1 billion years from now, if curious minds still gather to look outward, they will be working on questions we have not yet thought to ask. The strangest planets they study may be ones whose existence we cannot currently suspect. Worlds shaped by physics we have only begun to map. Worlds with chemistries we have only begun to model. Worlds whose shadows are too faint, or too brief, or too far for our small instruments tonight. For now, we sit with what we have. A long list of dim flickers, a longer list of suspected worlds, a still longer list of worlds we have not yet seen and may never see. The galaxy keeps its catalog of shadows, and we keep ours, and the two slowly come into agreement, one careful measurement at a time. It is a quiet kind of work, watching for the dimming of a star, waiting for the same dimming to return, listening to the universe through the smallest of clues, and trusting that the shadows we cannot yet read are still there, patiently waiting to be noticed. After so many strange worlds, it helps to step back and look at our own. Earth, in this wider view, is one planet among an uncountable number. The galaxy alone may hold hundreds of billions of planets. Most are nothing like ours. A few might be more like us than we yet know. Seeing the strangest worlds changes how we see this one. A planet where it rains molten glass makes our soft rain feel like a small miracle. A world tidally locked to its star, with one face burning and the other frozen, makes our gentle days and nights feel like a careful gift. A rogue planet drifting in the dark, without a sun to warm it, makes our quiet morning light feel almost impossibly kind. Earth is not the center of anything, but it is, by every measure we can take, deeply unusual in its balance. The atoms that make this balance came from far away. The iron in your blood was forged in the cores of stars that lived and died long before the sun was born. The calcium in your bones was scattered by old supernovae, the bright deaths of giant stars. The oxygen you are breathing right now was cooked inside stellar furnaces and blown out into space as those stars ended. Every breath is, in a real sense, a memory of ancient light. This same story plays out on every strange planet we have seen. The carbon that might form diamonds in the deep mantle of a far-off world came from the same kind of stellar death. The silicon in those sideways glass clouds, the iron in those rains of molten metal, the water on the possible ocean worlds, all of it traces back to stars. We share an origin with the strangest places in the sky. That kinship is quiet and easy to forget, but it never goes away. What remains unknown is how often the balance tips towards something like Earth, and how often it tips towards something stranger. One view holds that small rocky planets in gentle orbits are common, and that mild worlds with stable climates may be sprinkled all through the galaxy. Another view holds that Earth's calm is rare, the result of many small accidents lined up just right, the right star, the right distance, the right large moon, the right early bombardment, the right slow cooling. We do not yet have the data to settle this. The strangest planets we have found do not prove either side. They only show that the range of possibilities is wider than anyone once guessed. There is also a humbler thought folded into all of this. Many of the worlds we have called strange may not be quite what we think. Some signals will turn out to be noise. Some atmospheres will turn out to be artifacts. Some planets may not exist at all in the form we have drawn. The picture we are building of distant worlds is still rough, still smudged at the edges. We are looking through a thin keyhole at a very large room. The strangeness we see is real in part and uncertain in part, and we will spend many lifetimes sorting which is which. Even so, the view through that keyhole keeps changing how we understand home. Studying lava worlds teaches us about the molten youth of our own planet, when Earth's surface was a glowing sea. Studying superpuffs teaches us about the way atmospheres can swell and shrink. Studying ocean worlds beneath thick skies teaches us what life might need and what it might not. Each strange planet is a small mirror held up at a strange angle, showing us a piece of ourselves we could not see from inside. And under all of it sits the deepest, simplest connection. The same physics that shapes a tidally locked twilight world shapes the slow turning of your own night. The same gravity that holds a pulsar planet to a dead star holds you right now to your bed. The same chemistry that paints iron clouds in a distant sky paints the rust on an old gate near your home. The universe is not many different universes. It is one quiet, vast, patient thing, working out its possibilities in every direction at once. Earth is one of those possibilities. So are the glass rain worlds, and the diamond core giants, and the lonely wanderers. So are you, lying here in the soft dark, made of the same old stardust as all of it. The strangest planets do not push us out of the story. They invite us deeper into it, gently, with the lights low and the questions still wide open. And so we come to the quiet end of our long walk through the strangest planets ever found. We have wandered far tonight, past worlds of glass and iron, past oceans hidden under hot ice, past lonely planets drifting without any sun at all. Some of these worlds may be exactly as they seem. Others may turn out to be misreadings of faint signals, ghosts in the data that future telescopes will gently correct, the mystery of which remains open, and that is part of why the night sky is still such a kind companion. Picture, for a moment, a single world far from here. It spins slowly in the dark, a soft blue marble warmed by a small orange sun. Clouds drift across its face in long, lazy curls. A wide ocean catches the light, silver and still. Nothing on that world knows we exist. Nothing on that world knows we have been wondering about it. And yet, somehow, the wondering and the world belong to the same quiet universe. We do not know if such a world is out there. We hope it might be. The data is incomplete. The telescopes are improving. Some researchers believe a true mirror of Earth is within reach in the next few decades. Others suspect that every world we find will be its own strange thing, related to Earth only in distant ways. Both views can sit beside each other tonight, like two candles in the same dark room. Think of the rogue planets moving through the deep space between stars. They drift without hurry, carrying their own faint warmth, perhaps cradling oceans beneath thick ice. They are not lost. They are simply elsewhere. The galaxy is wide enough to hold them all, and patient enough to let them wander for billions of years. Think of the lava worlds with one side forever glowing. The wind on those planets may carry rock vapor across the terminator into the cold night, where it falls as strange, glittering snow. We may never walk there. We may never need to. It is enough that such a place can exist somewhere in the same universe that holds your quiet room, your soft pillow, the slow rhythm of your breathing. Think of the diamond worlds, if they are real, and of the puffed giants lighter than cork, and of the small egg-shaped planets stretched by the pull of their stars. Think of pulsar planets circling the corpses of dead suns in steady, ancient orbits. Think of the hidden moons that might cradle warm seas under crusts of ice. Places where the only sound is the slow creak of frozen water and the gentle stirring of dark currents far below. The universe does not ask us to solve it. It only asks, in its quiet way, that we keep looking. Each new telescope opens another small window. Each new measurement nudges some old theory toward truth or toward retirement. And in between the answers, there is this, the simple pleasure of lying still and imagining far places. You are very small, and the universe is very large, and that is a comfort rather than a burden. The same gravity that bends light around distant black holes also holds you softly to your bed. The same atoms that drift in faraway nebulae also rest within you, glowing in their own gentle way. You are made of the same patient stuff as the strangest planets ever found. You are not separate from any of it. Somewhere tonight, a young star is lighting up for the first time. Somewhere, a world is forming from a slow disk of dust. Somewhere, an ocean is rolling onto a shore no eye will ever see. These things happen whether or not we notice them. They will happen long after this night ends. They were happening long before it began. Let those distant worlds keep spinning in your imagination as you drift. Let the soft blue marble turn. Let the lonely wanderer move on through the dark. Let the diamond skies sparkle quietly. There is nothing for you to figure out now. The mysteries will keep until tomorrow, and the tomorrow after that, and all the tomorrows yet to come. The strangest planets ever found may grow stranger still as we learn more. Some will turn out to be ordinary in ways we did not expect. Some will turn out to be even more wondrous than we first guessed. The question stays open, and the open question is a gift. It means there is always something more to wonder about as we close our eyes. Rest now. The universe is vast and gentle and in no hurry at all. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.